NTRDMA version 0.1. And this is the very first release of this driver to the public, aka you guys. Don't worry about it. I'll just use the notes. So, I work at a storage company. One of the things that we do with our storage systems is we have dual node computer, and we have to do things like run an application on both and run reliably enough so that if one node fails, the other one can continue to provide the service without stopping. And the driver that I've been writing allows us to copy that data from one to the other. It's a similar problem that you have with a lot of other applications that need high reliability, high availability. So I have a lot of, there are other applications besides storage is what I'd like to say. The particular hardware that I'm using is called a non-transparent bridge, an NTB. I'll talk a little bit more about that on the next slide. It's a piece of hardware that we've long supported in EMC hardware to copy the data across, except that it's been supported by proprietary drivers, Windows drivers that have been ported to Linux, but running in user space and things like that. What I've done is I've replaced that part of our stack with a Linux driver that goes in through the OpenFabrics APIs. Are any of you familiar with RDMA or OpenFabrics? I see one. Very good. Two. So it's sort of like networking for clusters, or in this case it's a 2-node cluster. But it allows applications to do zero-copy data transfers from one node to another node in ideally a safe way, a hardware offloaded, so that the applications can run at high performance and with little overhead. We're doing this with NTB hardware, which is much more limited than, say, an InfiniBand card or Rocky over converged Ethernet card. So a lot of this driver is actually done in software. The reason that this is sort of important for today is, although we've had NTB devices in EMC hardware for years, today they're starting to come on the market in systems that you can buy off the shelf and use in your data center. So other companies may be interested in using this technology. And we would like to share what we've done at EMC with other companies so that together we can all make it better. I should say a little bit more about myself. So what I do at EMC is I work on prototypes. I see a technology for the first time and then have maybe a year or two to work on it, and then I move on to something else. NTRDMA is something that I'm planning to stick with for a while beyond this term, but for the past couple of years I've been involved in PCI Express, memory management, and RDMA. So, if there are anybody who are not just familiar with, but also specialize in RDMA, that would be very good to have. I need to talk to you after this. All right. So, NTB, non-transparent bridge. Does anybody know what a PCI Express bridge is? Okay. So, for those of you who may not be as familiar, in a PCI Express system, you're connecting your computer, your CPU, to a peripheral device, a PCI device or PCI Express device. And that can be done directly through a single PCI Express bus from the CPU to the device, or it can go through a bridge. An NTB is a non-transparent bridge because the CPU will not enumerate the devices on the other side of the bridge. All it can do is write to the bridge, and that write will be sent across the bridge to something else. In this case, on the other side of the bridge, there will be another CPU. So you can have one CPU write to the memory of another system through the PCI Express bus. That's what makes this sort of a networking technology. That's what enables RDMA. You can do things like DMA, which is direct memory access. Who's familiar with DMA? So you may have heard this in terms of a device driver or a hardware device that will have a DMA engine on it. What will happen is you provide a DMA address to this hardware so that it can reach into the CPU's memory, and if it's a network device, it can copy the frame data to that memory or read from the frame memory to send it out to the network. rather than having the CPU move all the data in small chunks. DMA allows you to offload the memory copy operations, and that's how I'm going to be using a general purpose DMA engine, which you give it a list of source, destination, length to copy data. And the way NTB and DMA are used together is that one of those addresses, in this case the destination address, will refer to memory on the peer. So you'll be copying from your local memory to the peer's memory. That is really, in essence, what NTRDMA is. It's giving that list of addresses. RDMA, I know there's one person in the audience or two people who are familiar with RDMA. This is the remote DMA. It's traditionally done with more expensive technologies like InfiniBand or RDMA over Converged Ethernet to use a device that can keep track of the memory in both systems or in one system, and then through some other addressing mechanism besides a DMA address, it will use things like memory regions to refer to the memory of the peer, and then the devices themselves will use some protocol and transfer the data, and then the receiving end will write it into its memory. So I hope you can see this. I'm going to point so that it's more obvious. This shows I'm not going to stand too close to the speaker though. This shows a stereotypical dual node system with two CPUs, a PCI Express switch or bridge, which connects a root port to multiple devices, which is what I talked about initially. This is sort of like a transparent bridge, one that can see the devices on the other side. There is a DMA engine, which is used for the general purpose DMA copy from source to destination. And there is a non-transparent bridge. And this itself looks like a PCI device, like one of these, as far as what the CPU sees. It acts like a bridge in that there is a PCI Express bus on the other side going to the peer. And in this configuration, each CPU node has an NTB associated with it. This is important for things like non-uniform memory, NUMA, where you have this CPU can access this memory very fast, but much slower going through an internode link to the other node's memory. And then again, much slower going through a bus to your peer storage server's memory, or any kind of server, really, your application servers. So I sort of touched on this in the title slide. What applications RDMA is useful for? Messaging, data protection. This is really what EMC uses it for. Data protection, copying. If you have a incoming write, you want to mirror that to your peer so that if either node goes down, both sides can continue with the most recent write cache data. Let's give it a second. I think it comes back, yes. Are people familiar with storage cache, write cache in that sense, where you have data that has been written, but because it's much slower to write to a disk, you keep it in memory until it can be committed to disk. So in this case, it's faster to reach the peer's memory, mirror the data there in case you can't get it to the disk in time. But you don't want to lose one peer in its memory because you can't reach across and get it out of the peer's memory when the peer is down. So, RDMA programming extraction. So this is the Open Fabrics API is what we're moving to. It had been a sort of proprietary equivalent messaging stack that enabled RDMA, but not through any open API. And I mentioned this at the beginning. Why is this important for now? Is because there are these new generally available systems that you can use in your data center. So we are transforming the EMC proprietary stack through using the NTB and DMA hardware. I wish I had stayed in order. I've already gone over this. If you don't mind, I'm going to go ahead. This is a much better picture of what I was trying to talk about. This is sort of the legacy stack that we've used with some of the driver names that we had used. And the most important thing in this picture is that we have our messaging application. this is what we use to tell the peer where cache metadata and cache data is in its memory. We say, we just wrote some data to you about this LUN, this address and this LUN, and it is in your memory now. And the peer can go and check some it, make sure it's correct, and respond. So there is a messaging part of this, and there is a data transfer part of this. The InfiniBand Verbs API can provide much the same messaging and data transfer. You can do a write, and you can do a send, and they have similar semantics to just bulk data transfer, and then interrupting the peer, sending a message. What we've done is basically replaced this whole chunk of the stack with open source simply by adding NTRDMA and then reusing the whole InfiniBand Verb stack, or minus the existing device drivers, but their APIs at the upper layer and at the lower layer, as well as the DMA engine APIs to access a general purpose DMA engine in Linux, and the non-transparent bridge APIs. And actually, the non-transparent bridge APIs, I have updated them in Linux. The current version of those APIs is one that I've re-architected, I suppose you could say, to allow multiple different NTB device vendors to provide their own implementations of an NTB device driver, as well as different applications. Before I made any changes in this driver system, there was only one possible application for NTB, and that was an Ethernet device driver. And it worked in a way of using a small memory window, and it would copy frames to a ring buffer, copy the ring buffer content to the peer across the NTB, and then send it back up the Ethernet stack. I suppose I should point out that NTRDMA uses a very large memory window so that you can write to any address in the peer's memory. So you can do things like zero copy. What might pass as zero copy in Ethernet, rather than copying an Ethernet frame into a ring buffer and then copying it back out into the network stack again, you can simply pass the address of an Ethernet frame and then write directly into it, and then give that frame back to the networking subsystem. So it's one less copy. For RDMA, you move that zero copy abstraction up to the application, so it is truly zero copy. It does mean, however, that if you're security conscious, you have to understand that having an NTB in your system, whether it's used for RDMA or not, allows a privileged driver, a privileged application, to write anywhere in the peer's memory without any way for the peer to stop it, unless you use some I/O memory mapping unit hardware. For instance, VTD, if anybody is familiar with this. It basically means that memory can only be written if it's been DMA mapped, and you may have some control over which devices can write to it. However, you will not have, say, the same safety guarantees if you can access the memory as you would with an InfiniBand device. However, going through the InfiniBand verbs, at least at a driver layer above the driver, it will be restricted based on memory regions and access control. If you have access below the driver, it is inherently insecure. So just in case you're security conscious. Another nice thing about using InfiniBand verbs here is that in addition to NTRDMA, there are other InfiniBand and Rocky device drivers that you may use. And this is one of the reasons that we wanted to do this, is because we can imagine having an EMC storage system that has multiple different interconnects between nodes of varying hardware. We may run on hardware that we have commissioned ourselves, or we may run on hardware without an NTB, for instance. Using an abstraction layer at this level allows us to do that. Using abstraction layers at this level allows us to use NTRDMA with different vendors supported DMA and NTB devices. And there's also one interconnect that I didn't show here with NTRDMA. Instead of using DMA engine and NTB, it also has a TCP backend, so that for simulation in, say, a virtual machine, if you're developing a product, the way we would use it is not invest in a whole lot of hardware for our lab space, invest in hardware for customers, but develop our applications and use the whole networking and RDMA stack in a virtual environment. It's maybe not as performant, but it's functionally equivalent with the TCP backend. Did I go forward backwards? Okay, so the NTB hardware interface. I talked about this on the last slide. This is the open source contribution that I've previously made to the Linux kernel. It is in as a v0.1, so that's fairly recent. That's only like a month and a half old, 2 months. The DMA engine interface, we currently use the Intel IO-AT DMA. There are other DMA engines out there. This is the hardware that we have access to in our labs. The InfiniBand Verbs interface has been around for a few years. Also supports other technologies, and we're adding the NTRDMA transport. So, again, I've already talked about the NTB and its contributions, but for reference, it used to support only the Intel devices. Now it may support multiple vendors. There's currently only an Intel NTB implementation, so if you know anybody who is a PCI Express bridge manufacturer, you may want to encourage them to write their own hardware driver for NTB. I know I am encouraging that. And the EMC contributions actually made use on Forenix. It was mentioned that these improvements went in. It went in the context that along with these changes, we also made some performance improvements to the existing Ethernet device driver in NTB, and we were able to improve its performance to something like 60 gigabits per second from whatever it was before. Okay, so NTB versus InfiniBand. One of the advantages here with NTB is that you go through a single bus. So you don't have to do any transformations between a PCI Express write. You may do a PCI Express write or several to transfer work requests to InfiniBand card. But in this case, what you're sending to the peer is just purely PCI Express writes and nothing else. There's no state kept in hardware, which you may see as a benefit or not a benefit. What we try to do is do as minimal overhead and as much offloading as we can to just have a list of writes that we want to send to the peer. However, you can also tell that with PCI Express, with the NTB devices that we are using, we can only support having one peer at this point. NTB is more limited hardware capability than InfiniBand, which is a fabric. It supports many, many peers. However, another benefit of PCI Express is that this is typically an internal connection in your system. So if you're thinking about manufacturing a product to give to your customers, the less things that the customer can poke and pull, the better. In terms of your support contract, you don't need to go and constantly say, oh, you pulled that plug, which is supposed to be our plug. You're not supposed to touch that. The customer may say, oh, that's InfiniBand? Whoop, I'm going to stick in my InfiniBand card. No, that will break things. So advantages, disadvantages to both. You may use a combination in some systems. So NTB only supports simple operations like write. This is RDMA implemented in hardware. So it uses the full work request completion work queues implemented in hardware. And in software, if we're going to do the same thing and implement queue pairs and work requests, we need to do what we can to mitigate that overhead. So I believe I will talk more about that in the next few slides. What are the capabilities of an NTB? We can write across the PCI Express bus, and we can interrupt the peer, and we have direct access to the peer memory. So the write, when we write to the peer, it's going directly into their memory without any CPU overhead on that side, just directly in the memory. There is one additional capability of an NTB, and those are the scratch pad registers. We basically use this just for initialization. Once we've initialized, we barely touch the NTB at all. We don't touch any of its device registers. I was going to give a demonstration at this point. However, with the network the way it is, with the internet the way it is, I am unable to do that, I'm sorry. But I was going to show that the systems that we have actually do work similar to the prototype that I showed at the beginning. They are dual node with dual NTB to appear. So you get multiple NTRDMA devices. Each of those devices is NUMA, so we get fairly good response times and latencies between the drivers. I was going to demo RDMA performance as well as Ethernet, because in addition to having an RDMA capability, if you don't have any general purpose networking, then you have no real way to address your peer. You can't use things like RDMA Connection Manager. And it's just generally useful to have an Ethernet device connecting the peers. So the NTRDMA driver supports RDMA as well as an Ethernet device in Linux. Okay, so to help those of you who are less familiar with RDMA come up to speed, an RDMA operation moves data from a source to a destination from one peer to the other. RDMA actually has different verbs to do this. There's a read, there's a write, there's a send, and there's a receive. It's typically done with zero copy. That's sort of the whole goal behind having RDMA in the first place, was being able to do this and offload the whole operation to hardware. So the way we do this in NTRDMA is by implementing the Q pairs, all of the setup of transfers and software, but then offloading as much of the actual memory copying to the DMA engine. We send it the list of source and destinations, and then let it go along with the CPU continues to do something else. Some of the interesting things about the NTB and the DMA engine is that things like the protocol overhead that we have is it's mostly affected by how many small operations that we have. So it's not just that you're offloading things, but you want to offload large data transfer operations. If you send it a bunch of small writes, like write this integer, write this integer, write this integer, that will take a long time for the DMA engine to reload a new request. Every time the DMA engine has to start something new, it takes some time. It can't read ahead very far. Also, we want to avoid a PCIe read, and this is for two reasons. Stability is one. Imagine you are doing a read. You've sent a read request across the bus. The peer root port has to respond. So this is a response in hardware. It doesn't interrupt the CPU or anything. But if the system goes down before it can return that response, hardware may behave differently. Different vendor hardware may crash. Different vendor hardware may send an interrupt, which may result in both peers going down at the same time. It's really something you want to avoid. But it's also a performance concern. If you are doing a read across the bus, using the DMA engine, which can really only read one thing at a time, you want those reads to be local. If you have to read across the bus, you can't move on to the next DMA operation until the first one is completed, or you can't go very far ahead. So if you have several reads across the bus, they'll get blocked up waiting for the previous one to finish. And maybe you can do it 2 at a time, but really not much more than that. So if you have your reads local, you'll be able to process them much faster. There will be less time between each transfer. So some of the RDMA resources. So these are typically abbreviated into memory regions, queue pairs, protection domains, and completion queues. And the important ones are memory regions and queue pairs. When your application is running, if it wants to have some memory to make available for the peer, it will register that memory, and that is called a memory region. What that implies is that applications are using virtual memory. The operating system may page this in, page this out, move it to a different physical location, and depending on which process is running, the pages may be used differently. So when you do a memory region registration, what that does is it pins those pages in memory so that they stay resident at some fixed physical address. In addition, it creates a DMA mapping so that the hardware, in this case the NTB device and the DMA engine, can refer to that memory using a DMA address. It basically allows you to access the physical memory from a device. These RDMA resources are created locally by the application. So an application will create a queue pair, it will create a memory region. And then in the case of RDMA, in the case of NTRDMA, because we don't have something like a InfiniBand device to track those resources, if you have the peer trying to send you something, the peer needs to know exactly where in your memory it's supposed to write that data. So in addition to creating these local resources, NTRDMA creates remote resources. And this is what's different about NTRDMA versus other RDMA drivers that have hardware. In this case, we have a remote memory region and a remote queue pair. So a remote memory region basically is the same as the memory region. It has the same information, except it's on the peer. So when the peer goes to do a transfer from its memory region to your memory region, what it will really do is it will go from its memory region to its remote memory region, copy from a source address to a destination address in the remote memory region, which refers to memory on the first side. So we'll do a write from MR to RMR. And I didn't talk about protection domains and completion queues. It's really sort of irrelevant for this, but there are no remote equivalents for those. A queue pair is really just the way that you send work requests right here, right there, send this message, or post a message to be received. So in addition to a queue pair, there's also a remote queue pair, so that if you're doing something like, say, posting a receive, the way sends and receives work is that you have to have receives posted by the peer in order to send. If you try to send and the peer hasn't posted a receive, it will fail. So a queue pair allows you to send a work request. It will receive into the next buffer that has been posted. A receive basically is sort of like a memory region, only it's a one-time use. It refers to a memory region destination that changes for each send. So here, these are how the memory regions are connected across the bus, MR to RMR, queue pair to remote queue pair. The memory region with its remote memory region equivalent. So each MR consists of a bunch of scatter-gather entries in a list. These refer to the pinned memory that has been registered by the application. The remote memory region also has a scatter-gather list. These refer to the addresses across the PCI Express bus that also refer to this memory. When you do a transfer, it is always in the direction of a local source to a remote destination. So if this side is doing a write or a send, it will be from a local memory region and its scatter-gather entries referring to this memory, to the remote memory region and its scatter-gathers entries referring to this memory. There is also actually a RDMA read, which I should mention while we're at this side. I said there's always a write operation here, but an RDMA read, this side is doing the read and it sends a work request, and the peer is the one who will turn that read into the equivalent of a write. This happens inside the driver, so where an InfiniBand card might be able to offload that entirely, because we have a software queue pair in this driver, it has to be done by the CPU. But it sets up the transfer and then offloads the transfer. So the overhead is actually not very large. The queue pairs and the remote queue pairs both process the same work requests. And that's important because if you're doing something like a send or a write, especially in the case of a send, the first side has to post a receive. That's posted to this queue pair, and the same receive is also posted to the remote queue pair. They have really the same information in them. So that later, when this side posts a send, it will consume a receive from this remote queue pair, note it in the work request of that send, perform the data transfer, then copy that send work request here, indicating which receive it consumed, and complete that receive on this side. So it comes out of this queue pair, and then the receive is completed into this queue pair, and we notify that the receive is completed on this side. Meanwhile, it says, okay, the send is complete. We need to make sure that it's synchronized in the CPU cache, in case your caches and your memory may get out of sync on incoherent systems. So then finally, when the RQP is done with it, it sends the completion back to the first one. So both the queue pair and the RQ pair, the remote queue pair, are involved in processing the work requests, always. The way this works efficiently is in terms of having ring buffers of work requests. The ring buffers really don't contain any data so much as they contain the metadata about the work request. It says this work request represents a send or a receive from a few sources and destinations. So we indicate which sources and destinations here. It's copied to the RQP, which sources and destinations. But by the time the RQP has that information about the send or other work request in its memory, it also has completed the data transfer. So the way this will work is we'll post a work request, carry out the work request on the sending side, receive the work request here, do any synchronization of buffers that we need to, and then complete. So each queue pair has a ring for requests and a ring for completions. And in order to avoid the small writes, which are the primary source of overhead, as much as possible, we copy all the data for several work requests, which tend to be large transfers, and then in a few small transfers, we copy the ring contents, an update of the pointer to the ring, and interrupt the peer. So there are a few small writes, but we do what we can to avoid them. The work completions, this is where the NTRDMA driver diverges from other InfiniBand drivers and how it processes completions. The completion rings belong to the queue pair, not the completion queue. But multiple queue pairs can complete into the same application completion queue. What happens is that when we interrupt the peer, we're notifying one of the completion queues that there are work completions to be pulled. Now those work completions could be for the send or receive queue of any of its queue pairs. So pulling the completion queue basically goes through all of the send or receive queues in all of the queue pairs. A queue pair may have a different completion queue for its send queue and its receive queue. So this is getting a bit technical, but we interrupt the peer by sending what's called a message signaled interrupt. We write basically a small amount of data to the peer, writing to its interrupt controller that generates an interrupt on that side. So we do this using the DMA engine rather than, say, the DMA is completed and then we do that small write with the CPU. The reason for doing that is that as the DMA engine is processing its work, it will have transferred some data, and at the end of transferring that data, it could interrupt the local side to say, I'm done transferring the data, and then continue. However, it's a little bit faster to just continue on with the next DMA transfer, and that next DMA transfer may just be a small one to write to the peer. And that write is sort of generic. It can be anything. We're just writing to the peer. We write a small amount of data, which happens to be the interrupt message to their interrupt controller. And the way we avoid too much of the small write overhead is simply by batching the request, as I said. So the small writes that we can't avoid in this situation are the update of the ring index, update of a virtual doorbell, which is basically just saying there are multiple things that might interrupt. We just have a way to say, one, you can check for certain completions or certain other completions or certain other completions. You don't have to check everything each time an interrupt arrives, even if you have only one interrupt signal. And then finally, delivering the actual interrupt. So for each batch of operation, each batch of bulk data operations, there are 3 small writes that we can avoid. However, the overhead turns out to be not that bad. We've been able to reach the maximum capabilities of the hardware that we have, which is fairly good. And the overhead, the CPU overhead using performance monitoring tools is really small. It's hardly anything. We're limited only by the hardware capabilities at this point. In addition to getting this to work at all, we have also done some technical workarounds of hardware errata. I'm not sure that, I'm just going to gloss over this because this is pretty technical. If you do certain things, even if they're in spec with the hardware specification, they may do things like lock up your computer. So we just try to avoid that. We use the message signal interrupt rather than the hardware doorbell register, which does the equivalent operation, except that we decide not to use the non-transparent bridge where we could use a NTB register. There is a TCP backend. The most interesting difference here is that rather than having a DMA engine hardware do the data transfer, we're doing it in software, in kernel space. You wouldn't use this in a performance setup, but you may use it in a product simulation virtualized environment setup. The real difference here is in the mapping. Instead of mapping user memory for a device to access, we remap user memory for kernel space. This is important because, as you know, processes can change which one is actually running at any time. So in order to safely do things in kernel space with user memory, you must remap it into kernel space. And that is really the major difference here. Once you have a kernel virtual address, you can pass it to something like a TCP send or receive, and receive directly into that. There are copies involved because it's through the TCP software stack, but it is functionally equivalent at the upper layers. So this is open source. I'm hoping that you guys will be interested enough to try this out if you have a product that could use it. And if you find that it helps you, if it would scratch one of your itches, that you would also consider working with me in improving this. I have a much longer list of things that might be interesting for anybody at any level or ability to consider for academic or other purposes as well. That's the end of my talk. I'm very eager to hear any questions that you have.
Okay, please wait for the microphone.
What hardware can be used with this driver?
Yes.
Please tell it explicitly. What.
So for instance, we use the Intel Sandy Bridge or Haswell CPUs, which contain both the DMA and the NTB hardware. Other manufacturers like PLX or Avago make PCI Express bridges, and I would like to encourage them to write a hardware driver for Linux that can do that. We have used proprietary drivers for both Intel and PLX.
And what if we have 2 NTBs in the system? Can we establish 2 or more NTBs in the system? Can we establish multiple peer-to-peer links from one system to other systems?
If you have multiple NTBs, you can. You would need to have, with this NTB hardware, because it has, the important limiting factor here is the number of NTB memory windows that it has. If you have an NTB hardware with many memory windows, it may be possible in the future to have a single NTB communicate with multiple peers. If you have multiple NTBs on the same CPU, then you could have multiple peers. It's really just a 1 peer per NTB. The reason you might want to use 2 NTBs to the same peer in the system that I showed is for NUMA. You want to use the NTB that is closest to the memory, rather than going across the inner CPU link, reaching the peer CPU's memory, going across the PCI Express bus, and then going back into the peer's other node memory.
And one more question. Can I, in principle, make a sort of chained configuration? Having two NTBs in the system, we can connect several systems in a chain.
Yes, so NTB device manufacturers have talked about ways that you can do that. Using the same hardware that we have, and also using newer hardware that is more fabric oriented. The newer hardware it's so much a different beast than this more limited hardware that I've been working with that this driver wouldn't be appropriate for it. But and maybe even in general, this driver wouldn't be appropriate for it, even if you chain them, as you say. This is another topology that's supported even using the hardware that I have used. But when you do that, you are probably not able to address the entire peer's memory in one window. You may only be able to access a portion of each peer's memory. So if you were going to do that, your application may have to copy into a transit buffer and back out.
Okay, thank you.
Okay, any other questions? Okay.
This is in regard to your the message signal interrupt messages.
Yes.
Since they're going across the bus, there's some sort of an NTB transaction. They're not actual PCIe message signal interrupts that are happening on the actual bus, correct?
Well, so a message signaled interrupt is really nothing more than a PCI Express write. It is the small PCI Express write from the device that lands. Its destination address is a register in the interrupt unit, in the interrupt controller of the CPU. If you look at a PCI Express device, if you do LSPCI as root and you add some verbose flags, you can see if it's configured for MSI, you'll be able to see the data and the address. And that is exactly the write that the device will issue.
So it's actually implementing a true MSI on the PCIe bus. It's now a message to the other controller, which will then pass it on to the CPU for actually doing the interrupt.
Yes, so once that message is received by the interrupt controller, it is transformed from an MSI into whatever interrupt the CPU supports, and that's really CPU dependent. It may be interesting to note that there are 3 different styles of interrupt on PCI Express. There is the traditional style, INTX, which is basically have an interrupt pin, right? And a device will just change the voltage on that pin and that triggers an interrupt. That's the PCI legacy way of firing an interrupt. The newer ways are MSI and MSIX. They are really essentially just a PCI write, just like any other data write. MSI and MSIX just have different configurations for where the data and address are and how they're configured on the device.
Okay. I was just confused. It seemed like that MSI was actually going to the other device, and then the other device was doing something with it as opposed to.
So, well, let me go back to whatever slide that was. How about this one? Is this large enough to see?
Yeah.
All right. So yeah, we're going to be sending an interrupt essentially from this CPU to this CPU, and that PCI Express write, that's all it is going to be emitted from this DMA engine. It's going to cross this NTB. That implies that the write is translated. Its destination is going to be translated from this NTB to an address on this bus. It's still just a write, however. It contains the same data. Its destination is this NTB. Again, it transits the NTB, and it has a new destination address coming up this internal PCI Express bus. These NTBs appear to be PCI Express devices. You just write to them, and the way they work is they transform that write across to the other bus.
Okay.
So that write, which is still just a write, lands in a register in the CPU. And that register happens to be the local APIC. And that local APIC is programmed by Linux when you register an interrupt with the driver, so that when that write lands in the register with the specified data, it will interrupt that driver.
Right. Okay.
But as far as what's on the bus, it's simply a small write.
Okay. One other question. All of this is going to be pushed to Open Fabric?
I'd like it to be. I feel like what I really need for that to happen is more community involvement. I could do it myself, and I have actually published this to GitHub. If you go to github.com/NTRDMA, I didn't put the URL on the slides because my feeling is that's a very informal address. I imagine in the long run this should live at some place like kernel.org or Open Fabrics.
Okay. Thank you.
Okay. Any other questions?
It seems that I started to understand the picture only at the end of the presentation, so forgive me if I missed something. Just a curiosity. Can you tell what is the maximum physical distance of this thing?
Well, that depends.
Between NTB and NTB.
So that depends. So if you want to run, say, a cable, like a copper cable between these things, you would use a physical retimer type of chip that basically allows you to set the desired distance. So if you're using PCI Express, typically your bus lengths are very short, just from the CPU to a peripheral device, right? You can't just connect a long cable to your peer, because at the physical layer, the signaling will be improper for that length. It's timing and
what is the actual length to which you can see how far apart can place to PCIes?
That I am not sure. The lengths that I have been developing on, they're internal bus, so they're maybe half a meter. Maybe even short, maybe a quarter of a meter. However, I have seen copper cables that are about 2 meters.
I understand. So other question was probably you can't answer it because it's too hardware thing. I see that this you're writing the block in sequence. You don't expect any replies from that part.
Right.
So probably this thing. Agree or disagree with me. But probably this thing, the limitations are only electrical. So from the timing point of view, you really can push them far apart.
Well, so from my perspective, it is write only. But from the PCI Express physical layer and data link layer, there is a transmission and a reply.
I see.
There is an acknowledgement.
So there probably is a timing. Thank you.
Yep.
Okay. Any more questions?
Anyway, as far as I know, you can use active optical cables for connections. So you could have about 100 meters.
That would be
nodes.
very good.
And the other question is, if you have 1 or 2 instances of the driver running on each node, because you have 2 circuits and 2 DMA engines and 2 NT bridges.
Yes. So there will be one instance of the driver when you load the kernel module once. However, it will probe for available NTB devices and create different device instances.
Okay, while we are thinking about the next question, I want to remind you that we have a presentation evaluation form in this notebook. So I asked you to fill this and left from the reception. Do you have other questions to Alan? Okay.
Okay, what can you say about write and read latencies? Are they comparable to PCIe?
So the read and write latencies that I wanted to demonstrate for you today are under 20 microseconds from if you're doing a round trip time. So send, receive, send, receive.
Fall.
Yes.
About polling, do we have any overheads due to constant polling of CPU?
There are two
CPU.
CPU overhead. Yes, there's more overhead than, say, InfiniBand because less of the RDMA implementation can be offloaded to the hardware. However, the overhead is not very large. Really, 10% of the CPU or something. Very small.
Okay, something from user space perspective. What software in user space have you tried in order to establish the connection?
So, EMC software and a utility called QPerf, which is just a simple performance analysis benchmark. It's what I use to come up with the numbers. There are improvements to be made in QPerf. For instance, it doesn't do any flow control between sends and receives, so it is possible for QPerf to starve itself of receives and then issue a send for which there is no receive and crash the Q pair. This can be worked around in NTRDMA quite simply by not processing that work request, waiting, trying again. However, it is perfectly valid and perhaps even appropriate for a lot of applications for the RDMA driver to simply fill that Q pair at the moment that the send is processed without a receive. I only changed that behavior because of QPerf.
Thank you.
Yeah. But since you asked about other applications, it is important to note that there are features that I would like community involvement. Other people who have an itch to scratch about using a particular application, especially open source applications with this driver. It doesn't support, or I haven't worked to try to get it to support completely the RDMA connection manager, which is used by a lot of open source applications to make connections between Q pairs. So things like NFS over RDMA or other application level or RDMA application level applications may not work out of the box without additional work. I don't know all of those or what they are. Really, my intention with the work I've done so far was to make this driver work in the first place, make it work with EMC product. But I'm definitely available to help other people make any changes or help them with the changes to make it work for their applications as well.
Okay, next question. Okay, if we have no any more questions, let's say thank you to all. So we are waiting.